Okay, so today we're going to do a little bit of review of exponential growth and decay in preparation for our test that's coming up. So before we get into the exponential growth and decay, let's just review a couple exponential expressions that need to be simplified. So while there's not necessarily a specific order in which you need to apply the different exponential properties, the way that I like to do it is I like to get rid of the parentheses first by kind of distributing that exponent to each piece of the product inside. And then after that, I like to get rid of negative exponents, and then I finish simplifying from there. So with that being said, this first piece here, I'm going to need to simplify first by getting rid of my parentheses. And I can do that by bringing that exponent of 3 to my 8, as well as bringing it to the x. So now I have 8 to the third times x to the third times 8 to the negative fourth power. Once I remove my parentheses, I like to get rid of negative exponents. And if you remember, the way to do that is to move the term with the negative exponent to the opposite side of the fraction bar. So the 8 to the third is going to stay on the top. The x to the third would also stay on the top, but this 8 to the negative 4 would have to go to the bottom, and now my 4 can become positive. Now, since I have common bases here on the top and the bottom with those 8s, I can simplify those a little bit more by dividing. But when you divide two common bases that are, two powers that have a common base, you subtract the exponents. Now, I always subtract the bigger exponent minus the smaller one. So in this case, that would be 4 minus 3. And I just make sure I put my final answer, which would just be 8 to the first, on the side that had the larger exponent, which would have been the bottom. Then my x to the third is still on the top. So my answer would be x to the third over 8. Moving on to the next question. Again, I like to get rid of parentheses first. So I'm going to bring this negative 2 exponent to each of my 3 terms. Now the 4 does not have an exponent, so it's now going to be 4 to the negative 2. The x, however, already had an exponent of a 4, so I have to multiply those exponents since one's inside the parentheses and one is outside, giving me x to the negative 8. And I'm going to do the same thing when I bring my exponent to the y. I have to multiply my 2 exponents here, giving me y to the negative 6. Now, all 3 of these have negative exponents, so all 3 of them are going to move to the bottom, or the opposite side from where they are, so that the exponents can become positive. And then at this point, the only thing I can do here is 4 to the second power is 16. So I can work that out. And then this would be my final simplified expression. And finally, number 3, there's no, so there is a parenthesis here that I'm going to get rid of. So this negative 2, so I have 1 over 3 to the negative 2 and x to the negative 2. Both of those are negative exponents, so I'm going to move both of those to the top, making the exponents positive, which leaves me with 9x to the second. Now, you definitely could have gone about doing that a different way than I did, but as long as you got the same answer in the end. Okay, next let's talk about writing rules for exponential functions. So if we remember, in order for it to be an exponential function, we need to have that a value be positive, and then we would look at our b value to determine if it's exponential growth or decay. So remember, if the b is greater than 1, it's growth. If the b is between 0 and 1, it's decay. And then you can put your function rule in the form of a times b to the x power. So looking at number 4, the first thing you want to look for is that a value, which in most cases here, it's going to be the y-intercept on the graph as well. So right here, I have an a value of 1. Now, the main thing I want to make sure is that it is positive. Since it's positive, this is an exponential function. So now I'm going to look for that b value, which is the multiple that's happening here. So 1 times 4 would give me 4. 4 times 4 would give me 16. 16 times 4, 64. And 1/4 times 4 is the 1. So my b value of 4 holds true throughout the whole table there. So because my b value is greater than 1, I know that this is going to be a growth function because it has a growth factor. So then I can write it in, y equals 1 times 4 to the x power. And you really don't need to have that 1 there. You could just have 4 to the x power. Okay, taking a look at the next one. So this one here, again, I'm looking for the a value, which will be my y-intercept here. And in this case, it is positive 1. Since it is a positive, then I know that this is an exponential function. So let's see, is it growth or decay? So let me find that b value, which is that multiple here. So it looks like they're decreasing. Okay, so let's look here. 1 times what would get me 1/6? Well, 1 times 1/6. And 1/6 times 1/6 would get me 1/36. But if you started out on the left-hand side, you might be thinking, well, 36 divided by 6 is 6. But remember, dividing by something is the same as multiplying by its reciprocal, which in this case would be 1/6. That means our b value is 1/6. That is a number less than 1, but greater than 0, which means this would be a decay function because b is a decay factor. So then we can write it, y equals 1 times 1/6 raised to the x power. Again, you don't need to keep the a value in there with the 1 because it's not going to change anything. You multiply something by 1 in the end. So if you just wrote 1/6 to the x power, that would also be sufficient. Okay, so now we're going to complete some tables of values here, and then we're going to graph the function, identify the domain and range. Okay, so for this first one here, we want to find our a value, which would be 1. We know the b value here is 1/4, which tells me this is going to be a decay problem. So now since my a is 1, I know 0, 1, that's my y-intercept. If I want to do 1/4 to the first power, I would get 1/4. 1/4 to the second power would be 1/16. And if I had 1/4 to the negative 1 power, so like this, that would flip that, right? So just give me a 4. And if I had 1/4 to the negative 2 power, that would give me 4 squared over 1 squared, which would be 16. Okay, now, for all of these types of exponential functions, your domain is going to be all real numbers every time because there's no restriction as to what numbers you can plug in for x. Your range, however, will be something more specific than that. So let me graph this. So negative 216 doesn't fit, but negative 1, 4, 0, 1, notice that that is our y-intercept, and 1, 1/4, and then 2, 1/16. So hold on with this. So this is what our decay function looks like here. Now, my range, notice either on the table or on the graph, the entire graph is above the x-axis and all of the positive y values. If you look at the y values on the table, they're all positive, which tells me my range is y is greater than 0, or you could say all positive real numbers. All right, so we're going to do the next question, but we're going to now play around on the graphing calculator. So to use the graphing calculator, hopefully you have that extension on your Chromebook if you don't have a handheld one. So when you go to your graphing calculator, the first thing you want to do any types of graphing is go to that y equals. Now, I'm going to clear that for a second. This is where you type in the equation exactly as it's written on the paper that I've highlighted here, right? So 4 times 2 to the x power. So 4, parenthesis 2, close the parenthesis, raise it to the x power. And your exponent key is this one just to the right of that alpha key. Now, if you go to graph, you will see this should be a growth function. We have a growth factor of 2, and it is. And if you go to second graph, you will get your table of values. Let's see if this worked. And then you can use these arrow keys to scroll up and down if you need to get, to numbers that you're not seeing. So starting with the -2, since that's the table on my paper, -2, 1, -1, 2. Oops. So we would have a 1, a 2, then the 0 was 0, 4, which we should know because the A value is 4 there, right? And so that should be your y-intercept, and then this B value here indicates growth because it's your growth factor. And then we have 8 and 16. So now you didn't really have to think too much to get all those points. You could just get them off that table on your calculator. If not, you would have had to substitute them all in for x and solve for y. So now -2 and 1, -1 and 2, 0, 4, 1, 8. So this is what our function looks like. It is a growth function. Therefore, the domain would be all real numbers. In our range, again, they're all positive values here for y. You can see the whole graph is above the x-axis where all the y's are positive. So you could just write y is greater than 0, or you can say all positive real numbers. All right, so we'll do the next one. Again, we'll practice a little bit with the calculator so you can use that as an option. So for this one here, before I actually go ahead and graph it, and we'll take a look. So my A value this time is 1 because you don't see anything in front of the parentheses, right? So we know 0, 1 is going to be our y-intercept. Then the B value here is 2/3. And since that B value is greater than 1, or sorry, greater than 0, less than 1, that tells us that, again, this will be a decay function. So if I want to get my table filled out on the graphing calculator, I could either do this by hand or on the graphing calculator. So I go to my calculator, go to y equals, clear out the previous equation. Now this one was a fraction, so we're going to do parenthesis 2 divided by 3 parenthesis, and then we're going to raise that to the x, which is this variable key here. Graph it if you want to see it as a decay function, which we're expecting. If you go to second graph, you will get that table. So going down to the -2, we have 2.25. Then we had 1.5, 0, 1, and then it would be 1.67 and 2.44. 0.667 and 0.44. Now if you did it by hand, 2/3 to the first power would just be 2/3. 2/3 to the second power would be 4/9. So you could have it written that way as well. Same thing if you're inversing it. This would be 3/2, or this one would be 9/4. So when we go to graph it, -2 and 2.25, -1 and 1.5, 0, 1, that's our y-intercept. 1 and 2/3 or 0.67, and then 2 and 4/9. And you can see our decay function here curving downward. Again, our domain for these is always all real numbers because there's no restrictions on what you can plug in for that x value. The range, however, since the entire graph here is staying above the x-axis, all the y's are positive. So you could say y is greater than 0, or you can say the range is all positive real numbers. All right, now we'll do this one here. Now this time, your A value is a -2. Therefore, this is not an exponential function. So it's not exponential growth or decay. All right, it's just like a theoretical function. We can still graph it, however. Okay, so just to show you on the calculator, this negative will make the graph be underneath the x-axis, which is why it's not exponential growth or decay. So if I go to type this one in, I would have negative 2 times 4 raised to the x. Just make sure I type that in correctly. Okay. So if I go to my graph, you can see because the a value is negative, the entire graph is below the x-axis, which in reality wouldn't make sense for objects or money or things like that. So that's why this is not exponential growth or decay, but it's still a graphable equation. So going to my table to get points, just to plot them, negative 2 is negative 0.125. And we have negative 0.5. And negative 2, then I believe that was negative 8, and then negative 32. So we can still graph it. Negative 2 and negative 0.25 will be just under the x-axis there. Then negative 1 and negative half. 0, negative 2 is still your y-intercept there. 1, negative 8 will be down here. And your graph would look something like this. Okay, now domain would still be all real numbers. But this time your range, since the whole graph is below the x-axis and all of these values are negative, it would be y is less than 0 or all negative real numbers. Okay, so doing a couple application problems now. So we have growth or decay, which is the first thing you have to decide, right? Is this a growth problem or is this a decay problem? So let's read through and see what information we could find. You deposit $600 in a savings account. So we're saving money, which I would think means it's going to grow, and it's going to earn 3.5% interest. So we know that this is our A value here because we're starting with $600. The fact that it's a savings account tells us this is going to be a growth problem. And 3.5% interest, right? If we move this decimal over 2 places, then that means the R equals 0.035. So the growth model or formula is A times 1 plus R raised to t. So your growth factor you achieve by adding 1 to the rate written as a decimal. So for this problem, we substitute in our values. The initial amount we started with was $600. Then we have 1 plus our rate to give us our growth factor, because this will now be a number bigger than 1, because we're going to have 600 times 1.035 raised to t. This is our model, okay? After we find the model, now let's find the value of the account after 7 years. So that's just a fancy way to give us that t value that they want us to substitute in here. So you're going to substitute in your t for 7. So using a calculator. So to get out of this screen, you're going to hit second quit. So now we can do 600 times 1.035 raised to 7, since our t was 7. And this is in money, right? So this is $763.37. $763.37. All right. So let's take a look here. You buy a car for $13,000. It depreciates at the rate of 12% per year. So depreciate means that it's losing value, and so this is going to be a decay function. The A is that 13,000, that initial value, and then the 12% is going to be written as 0.12 for our R. So the decay function is A times 1 minus R, and that's because this needs to give us a decay factor of a value less than 1. So when I put the numbers in, I'm putting in the 13,000 for the A, 1 minus 0.12. Now if I simplify that, 1 minus 0.12 is 0.88. Now notice that that is a number that's greater than 0. right? So the b has to be less than 1 and greater than 0. 0.88 does follow that. That's why it's a decay factor. This is my model right here. Now I can use that model to find the value of the car after 5 years. So my t is 5. So on my calculator, I'm going to plug this in, putting in the 5 for the t. So I have 13,000 times 0.88 raised to 5. My new value after 5 years is 6,860, and then that would be 52 cents. So 68.60, 52. 68.60, 52. You always round to dollars and cents when you're dealing with money. All right, and I think that's it for our review for exponential growth and decay.